Thanks for joining me for another lecture on fuel cells. Last lecture, hopefully you didn't miss it, but it was just a review of thermodynamics that will help us in this course. Now let's talk about some little bits of, I would say, chemistry, physics that you may or may not know if you're taking this course from me. Probably do, but let's remind you of it. First of all is a mole. What is a mole? A mole is a great little mammal. But a mole is also a measure of quantity. What do I mean by quantity? I mean a count. So there is one mug. These are 3 items. And if I want to describe these 3 items, I could say a trio. And a trio is a word that commonly means 3. If I go and grab a dozen eggs, the word dozen is commonly used to describe 12 of something. If I say baker's dozen, then where I'm from, baker's dozen is a word that is commonly refers to 13 items. What about a pair of shoes? That typically means 2 shoes. So I mean a count. 1, 2 shoes is called a pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is called a dozen. Now, if you count more items, I want you to count 6.022 times 10 to the 23 items. If you count that many items, you are counting another special name. It's called a mole. So a dozen means 12, a pair means 2, a few or a trio means 3, baker's dozen means 13, and a mole means 6.022 times 10 to the 23. That's all a mole means. It's a count. It's a quantity of substance. Now, if I were to count a mole's worth of cars, they would take up a lot of space. It would mean that I have counted 6.022 times 10 to the 23 cars. If I were to count that many cell phones, I would count 6.022 times 10 to the 23 cell phones, and it would take up less space. What we usually use mole for, though, is like chemistry, physics. So we're usually measuring 6.022 times 10 to the 23 of small things like electrons or ions or molecules or things like that. So it's hard to count them because we can't really see things that small, right? But right now, I just need you to know that a mole is a count, and there are 6.022 times 10 to the 23 of them. There's a special name for 6.022 times 10 to the power of 23. We name it after the dude who invented it, and his name is Avogadro, so we name it Avogadro's number. So if you want to sound really nerdy, you could say there's like so much dust in here. It's like Avogadro's number versus pieces of dust on my desk. There probably are Avogadro's number pieces of dust on my desk. 6.022 times 10 to the 23. It just means, whoa, there's a lot in there. All right. Now, there's a thing called molar mass. Molar mass. And the molar mass is the amount of mass that in kilograms. It's the amount of mass in kilograms that each mole of a substance will take up. So I have, let's say, I have 6.022 times 10 to the 23 cars. What's the mass going to be? Lots and lots of kilograms. I have 6.022 times 10 to the 23 particles of dust. What's the molar mass? Probably in the less than a gram, right? So a molar mass is take all of the molecules, count them up to Avogadro's number, 6.022 times 10 to the 23, and then see what its mass is. And that is called the molar mass, and we also call that molecular weight. It's, as an old person, it's found in the back of textbooks. As like a young person, it's a published number that's available on the internet. basically somebody calculated it. Somebody did that count and calculated it. It's available for you, and it's probably done by a poor PhD student who had to spend their time doing that. And it's readily available to us. Now, there's this thing called atomic mass units, AMU. The atomic mass units are set based on a certain substance. And if you were in my class, I would ask you to take a moment and look at this lecture note and make an informed decision of what kind of substance is one atomic mass unit. So atomic mass unit, I say here, is 6.022 times 10 to the 23. That should ring a bell. That's Avogadro's number. We just talked about that. It's a mole. So I have a mole of something. And if that mole of that stuff weighs 1 gram, maybe it's dust. If it weighs 1 gram, well, let's not call it a gram. Let's call it 1 AMU, just to be confusing. We didn't have to do that. We could just have the count and the grams, which is kilograms basically. But we also want to call that an AMU. We want to call 6.02 times 10 to the 23 an AMU. It's selected so that 1 gram equals numerically the mass of a molecule expressed in AMU. But which molecule? Well, let's look at this. The molar mass of hydrogen is 2 AMUs. Of hydrogen, H2 is 2 AMUs. A molar mass of H2 is 2 AMUs. So 1 mole of H2 is 2 grams of H2. Okay, it's 2 grams of H2. So then what's the AMU based off? It's based off hydrogen. If 2 of them are 2 grams, 1 of them is 1 gram. AMU is based off the atomic mass, or the mass that a hydrogen atom is. And if you take 6.022 times 10 to the 23 of those hydrogen atoms, then they're going to have a mass of 1 gram. Of H2 atoms, of H2 molecules, it's going to be a mass of 2 grams. Why is this better? Why is the AMU useful? I don't think it's useful to call it an AMU. Maybe other people do for a different reason, but it's useful to know how many grams are in an AMU. So now if I go and I measure grams of hydrogen that I have, now I have a measurement method. I'm talking real world. I can see how many molecules I have based on the mass that I literally have in front of me. Same with water. Now water, you can imagine because you can see water. So here's the water. It's sitting here. If this amount of water weighs 18 grams, then I know I've actually counted 6.022 times 10 to the 23 molecules in there. So I can't see those molecules, but I can weigh how many, or take the mass of this amount that I have, see how many 18 grams are in my hand. And if there's 1 times 18 grams in my hand, I've got a mole of water. So you see how we're getting practical now. We have a measurement way of counting molecules that we can't see, which is great. All right. So now I've talked about the count, and I've talked about how much mass is in that count. We know how many grams. Then that's an atomic mass unit. We can relate directly to the number of moles. So I know how many molecules made that mass happen. Now let's talk about molar volume. The molar volume is the meters cubed, the amount of space it took up in volume per mole that I counted out. Let's think about cars again. I'm going to count out 6.022 times 10 to the 23 cars. They're going to take up a massive volume. I'm going to count out 6.022 times 10 to the 23 pieces of dust on my desk, that's going to be a teeny tiny volume in meters cubed, right? So the different substances take up different volumes, but different substances in different states take up different volumes as well. Because if I want 6.022 molecules of water that are gaseous, it's going to be a big volume. 6.022 molecules of water that are in a liquid form is going to take up less volume. So the molar volume depends on its state. The state depends on normally pressure and temperature. So the molar volume, yes, you can look it up, but then you can look even further. Well, what state? So a molar volume is published because PhD students have done the work to quantify the amount of volume that a certain count, 6.022 times 10 to the 23 of molecules take up. And they've done that at different pressures and temperatures in different states as well. So make sure that you look at the fine print of whatever table you're looking at the back of a textbook. I sure love to show you my textbooks on this. I remember looking up the tables myself. But anyway, if you look it up, even online, make sure that you use the right value. And don't really trust AI. It's not very good at stuff like this. It'll find the easiest value. Okay, so molar volume is the meters cubed. It's how big that space is when I counted out a mole of these. So I have a diagram about it here. I've counted 6.022 times 10 to the 23 of something. I've put it in a vessel and it made this amount of meters cubed. So molecular volume is the volume over the number of moles. Now, I can convert that to molecular mass over mass density because let's look at, like, why is this equal? Why is Vm equal to molecular mass over molecular density? Let's do it. Molecular mass over density. Molecular mass is the amount of kilograms in each mole we talked about. And the density, we should know. If we don't know density, I probably have a video on it. If not, leave me some comments below and I could talk to you all day about what mass density is. But it's mass density. It's how much mass is there in like a cube of a meter cubed, right? Might be a lot of mass, might be something light and there's not a lot of mass. So anyway, kilograms per mole over kilograms per meter cubed. Now this is in the denominator, so I'm going to switch it to the numerator by flipping it. And I'm going to cross out kilograms, and what I'm left with is meters cubed per mole. Meters cubed is volume over mole. So molecular mass over mass density is the same as molar volume, which is volume per moles. Very useful relationship. And so how I can use this is I can rearrange this formula. It makes sense that the molecular volume is the volume per mole, but let's rearrange that. Now we have number of moles is the volume that stuff's taken up divided by the molecular volume. So if it takes up 3 meters cubed and the molecular volume is 1 meters cubed, then I know I have 3 moles of the substance. So now I can go to the real world and I can measure, I can collect a volume in meters cubed of a stuff divided by the molecular volume that those PhD students calculated and tabled and made available to you. And now I know how many moles is sitting in my vessel. I know how many moles is sitting in here because I know its volume and I know what it is. It's a material property, the molecular volume. So is molecular mass. So that's really exciting. All right, that's molar volume. Last thing I'm going to teach you to get ready for calculations in fuel cells is let's remember that electrons are a thing. Electrons are a very useful thing. Electrons are what we make fuel cells for. When electrons move, it's electrical energy. electrical energy is very, very useful because we can transfer it into other forms of energy. Faraday is a dude who spent time at his desk counting electrons. Faraday noticed that if he counts 6.022 times 10 to the negative 3, that's his buddy Avogadro's number of electrons, then he can multiply them by his other friend's number, Mr. Coulomb. These were all misters at the time. It's a historical thing. So Mr. Faraday said, I'm going to take Mr. Avogadro's number and I'm going to multiply it by Mr. Coulomb's number. And that'll give me the amount of charge for that number of electrons. If they're moving. If they're not moving, then they're going to give no charge. And he called that Faraday's constant. So charge equals N times E is what I'm showing you on the screen here. Charge equals N times E. N is the number of electrons. And so we're going to say 6.022 times 10 to the negative 3. That's our number of the day. And if we take an Avogadro's number of electrons and we multiply it by the charge on each electron, how do we know that the charge on each electron is 1.602 times 10 to the negative 19? How do we know that? Did I teach you that in fuel cells? In this fuel cell course? No, I didn't. But it's a fact, as I said here, it's a fact. You know where I teach you that? I teach you that in my magnetic circuits class, which is also posted. And it has to do with an magnetic field inside the measure of a magnetic field spanning a certain distance for a certain amount of making a certain amount of magnetic force in a vacuum over a certain distance. And that's what a Coulomb is. So at any rate, it's a fact that that's how much charge is on every single electron. So that's a teeny tiny amount of charge. That's not a lot of charge. 1.602 times 10 to the negative 19, very, very tiny number of charge per electron, times a massive number of electrons I'm going to pick for this problem. And when I multiply the two together, I get quite a lot of coulombs. Again, coulombs are a measure of charge. Charge is useful. 96,485 coulombs. It's a famous number, 96,485. It's a famous number, and it's called Faraday's constant because Faraday didn't want it to be called the Avogadro Coulomb number. So there it is. Faraday's constant is N, number of electrons, times the charge on each electron, which is 96,485. I'm leaving it at that for this video because we can pick that up next day and say, we liberated these electrons and used them again. We put them through a parallel path or through a spatially separated path that is joined with copper, which is a wire. And look how much charge I'm sticking through that wire. Let's calculate how much hydrogen we consumed. Then we can calculate how much electricity we produced. And that's where we're going with the next video. Thanks so much for watching. Please put your comments below. Tell me, how do you like it? Is it easy? Is it hard? Is it interesting? Is it super boring? Thanks so much.